Today we will be discussing coke requirement for modern blast furnaces. We'll explore the evolving role of coke in iron making, especially under high productivity condition, and outline key quality parameters and degradation mechanism. Coke is a strong, non-melting carbonaceous material essential for iron making. Modern blast furnaces are trending towards high pulverized coal injection rate exceeding 200 kilograms per ton of hot metal, which reduces coke consumption to below 300 kg per ton hot metal. This shift demands higher coke quality to withstand mechanical, chemical, and thermal stresses. Our objective today is to outline coke's function, quality parameters, degradation processes, and specific need for high productivity operations. Coke serves multiple critical roles in blast furnace. It provides heat, acts as a structural support, and serves as a reducing agent. Key quality parameters such as strength, size, and reactivity are vital for furnace stability, especially in high productivity operation where coke degradation can impact efficiently. Let's break down coke's role. It generates heat, it provides structural support for the body, and it produces reducing gases, it enhances permeability and resistance in lower zone. It supplies carbon for carburization. It acts as a filter for soot and dust. Each function is essential for smooth and efficient furnace operation. High quality coke typically contained 87 to 92% fixed carbon, which is crucial for strength. Ash content should be below 8 to 12% as it replaces carbon and increases slag volume. Sulfur must be controlled via value in use calculations, and volatile matter should be uh, low to support high PCI rate. Key quality requirements include large stable particle with a narrow size distribution, high resistance to breakage and chemical attack, and sufficient carburization ability. Acceptable range include an average particle size of 40 to 60 mm, a CSR greater than 58 and CRI below 29. As the coke enters the blast furnace, it undergo a several degradation processes, thermal breakdown due to heat, physical breakdown from mechanical forces, and chemical reactions. High PCI rate accelerate these processes, especially coke descent through the different furnace zones. Coke degradation occur in several zones: the granular zone, cohesive zone, raceway, and hearth. Each zone presents unique challenges that contribute to overall coke breakdown. In the cohesive zone, coke faces mechanical wear from softening, melting uh, material, and chemical degradation via CO2 gasification. High temperature here accelerate coke consumption and carbon monoxide production. In the raceway, coke experiences graphitization due to high temperature, thermal shock from rapid heating, and high velocity impact. These factors contribute significantly to coke breakdowns. Optimal coke size is between 45-55 mm with a narrow distribution to minimize fines. Proper screening increases voidage, enhancing permeability. The harmonic mean size is a key indicator of gas flow resistance. Cold strength is measured by a tumble test, while hot strength assessed through CRI and CSR. Higher CSR and lower CRI are essential for stable operation under high PCI rate, as they reduce fines generation and maintain permeability. The coke degradation is a cone-shaped zone in the hearth that must remain permeable to allow gas, slag, and metal flow. A clean active deadman is indicated by good carbon saturation and drainage. Inactivation can lead to poor distribution and short taphole life. Remedies include using larger, stronger coke and reducing PCIe. At high PCI rate above 200 kg per ton of hot metal, coke consumption drop below 300 kg, but coke must withstand higher load and longer resistance time. Key requirements include high CSR, large coke size, and strategic use of nut coke. Benefits include reduced direct reduction, but challenges like increased fines must be managed through improved coke quality,